Einstein was afraid of something. Not the atomic bomb. Not black holes. Quantum mechanics. Because quantum mechanics said, two particles can be on opposite ends of the universe, and when one changes, the other changes instantly, with no delay whatsoever. Einstein called this spooky action at a distance. And he said, this is impossible. Nature cannot work this way. But he was wrong. Quantum entanglement is real. It's been tested. It's been measured. It won a Nobel Prize in 2022. And the thing Einstein feared became the fundamental fabric of reality. In 1935, Einstein published a paper. The title was simple, but the content was devastating. Can quantum mechanical description of physical reality be considered complete? His answer, no. According to Einstein, quantum mechanics was an incomplete theory. It was missing something. Because quantum mechanics proposed something like this. Two particles interact. Then they separate. One ends up on Earth, the other on Mars. Now you measure the Earth particle. Spin up. Okay. Quantum mechanics says, at that moment, the Mars particle instantly becomes spin down. No delay. No speed of light limit. Just instantly. Einstein said, wait. This is nonsense. Because if the Mars particle changes instantly, that means information is traveling faster than light. But relativity says nothing can go faster than light. So either quantum mechanics is wrong, or relativity is wrong. They can't both be right. Einstein's solution, quantum mechanics, is incomplete. There must be a hidden mechanism underneath. A cause, an explanation, a connection. The particles must have learned their spin states at the beginning. One up, the other down. Then they separate. Measurement just reveals what was already determined. Hidden variables. Einstein believed in them. But quantum physics said, no, there are no hidden variables. The particles don't have spin states until measured. Both are simultaneously indefinite. And at the moment of measurement, both instantly become definite. Einstein couldn't accept this, and he spent the rest of his life fighting it. In 1964, 9 years after Einstein died, a physicist named John Bell discovered something. A test. An experiment. Einstein or quantum mechanics. Bell wrote a theorem. If Einstein is right, if hidden variables exist, then certain measurement results must follow a specific inequality. Bell's inequality. If quantum mechanics is right, that inequality will be violated. And here's the beautiful part. It's testable. You can do an actual experiment. Take two particles. Entangle them. Separate them. Measure in different directions. Count the results. If the numbers follow Bell's inequality, Einstein is right. If they violate it, quantum mechanics is right. In 1972, the first experiment was done. Results: inequality violated. In 1982, a better experiment. Violated again. In 2015, a loophole-free experiment. Every possible escape route closed. Same result. Quantum mechanics was right. Einstein was wrong. Two particles really are connected. The distance between them is irrelevant. When you measure one, the other responds instantly. No hidden variables. No hidden mechanism. Just this, entanglement. Okay, but what does this actually mean? Most people think of it like this. Two particles are somehow linked. You poke one, the other feels it instantly. But that's not quite right. Because nothing is traveling. There's no signal. There's no information transfer. Here's the really weird thing. The two particles aren't actually two separate things. They're one quantum system, even though they're separated. Let's try a metaphor, but be careful because all metaphors fail. Imagine two coins. One shows heads, the other shows tails. You put them in different boxes. One box on Earth, one on Mars. Now you open the Earth box. You see heads. Instantly you know, the Mars box shows tails. This isn't surprising, right? The coins were like that all along. You just didn't look. Einstein said, particles are like that too. The spins were determined from the start. We just don't know until we measure. But quantum mechanics says, no, particles aren't like coins. Before the boxes are opened, both coins are both heads and tails. Simultaneously, both of them. And the moment you open one box, both coins collapse into a state. If Earth is heads, Mars becomes tails. Instantly. Distance irrelevant. But wait, how does this not send information? Because you can't control which result you get. You can't choose for the Earth coin to be heads. It's random. So you can't send a message to Mars. You can't transmit a code. What you get is correlation, consistency, but not communication. That's the weirdest part of quantum mechanics. Something happens instantly, but information doesn't travel faster than light. Einstein hated this because it makes no sense. But nature doesn't care about our sense. Now you might say, okay, this is weird. But what's the practical importance? A lot. Quantum entanglement is no longer just a theoretical curiosity. It's the foundation of technology. Quantum computers. Normal computers work with bits, 0 or 1. Quantum computers work with qubits, both 0 and 1, simultaneously. And qubits can be entangled. This allows them to solve certain problems exponentially faster. Cryptography, drug discovery, materials science, climate modeling, quantum cryptography. If two parties share entangled particles, they can create a communication channel no one can eavesdrop on, because any attempt to measure breaks the entanglement. Instantly detected. Quantum teleportation. No, not like Star Trek. But you can transfer the quantum state of one particle to another particle using entanglement. All of this comes from the idea Einstein said was impossible. And here's the most ironic part. Einstein is the father of relativity. He proved that time and space are relative. He showed that nothing is absolute. But when quantum mechanics came along, he wanted it to be absolute. He wanted determinism. He wanted cause and effect. And the universe said, no. At the deepest level, the universe is indefinite, probabilistic, entangled. Einstein couldn't accept it. But science did. In 2022, the Nobel Prize was awarded. Alain Aspect, John Clauser, Anton Zeilinger, for experimentally proving quantum entanglement. Einstein was wrong. But being wrong taught us one of the most important things. Nature doesn't care about our intuitions. Here's the summary of the story. Einstein hated quantum mechanics. Because to him, it was incomplete. There must be hidden variables. There must be local reality. God does not play dice, he said. But Niels Bohr replied, Einstein, stop telling God what to do. And in the end, experiments were done. Bell's theorem was tested. The results are clear. Entanglement is real. Local reality is not. Two particles can be on opposite sides of the universe and still be one system. When you measure one, the other responds instantly. No hidden mechanism. No hidden variables. Just the strange, counterintuitive, dazzling structure of quantum mechanics. And Einstein, at the end of his life, never accepted it. But science did. Technology did. And now quantum entanglement is building the future. Quantum computers, quantum cryptography, quantum networks, all built on spooky action. So yes, Einstein was wrong. But even being wrong taught us something. The universe is stranger than we thought. Deeper, more connected. Distance might be an illusion. Separation might be an illusion. At the quantum level, everything is entangled with everything. And once you see that, everything about reality changes. Einstein saw something to fear. But what he actually saw was the foundation of the universe itself. Spooky action 1. And now we're learning to live with it.